Okay, so what is the dot product of u times w? The given w vector was w, and then we have u. What's the scalar here? When you multiply u times w? I got 11. So are they orthogonal? No. How about v times w?
Yes.
Yeah, you get 0, and so this is a yes. You can move on. Given an initial point and a terminal point, find vector w and then determine if these vectors u or v are parallel. How about vector, well, first of all, what's vector w? 2, 4, 1. And so then how about compared to vector u? Is u a multiple of w?
Yes.
Yeah. And so then are they parallel?
Yes.
Yeah, so you could say it this way, u over 2 is equal to w, or you could say u is equal to 2w. Either one. So since one is a multiple of the other, then yes, they are parallel. What about v? No. So some constant times v is not equal to w, so no. Okay, so far, like, nothing super amazing or exciting, just learning how to function with your vectors in 3D. Okay, now where things start to get interesting is when you talk about direction angles. Okay, and this one's a little bit hard to visualize, so we'll just do our best here. Okay, so let's say that you have a non-zero vector. Let's call it vector m. And vector m, I can write in ijk form. So here I have this non-zero vector where a, b, and c are just some constants. So this vector, if I graph it in 3 dimensions, right, I'm graphing an x, a y, and a z. So it's a vector that's coming out at you in space. Now this vector makes some angles, alpha, beta, and gamma, that are angles between 0 and pi with I, j, and k respectively. So these angles here are called the direction angles of vector m. And their cosines are called, this is so stupid, but they're called the cosines of vector m. Okay, so let's see if we can visualize how this works. So if we draw our axes, here's x, here's y, here's z. Okay, so I have vector m, and it's coming out towards us into this first octant. So if we just kind of draw our a little box. Oh, this is going to be a hard picture to see. Yeah, that's better. Okay, so there's vector M, which is going from the origin up to this corner that's coming out at you. So here's vector M. Okay, so this vector makes angles alpha, beta, and gamma with the unit vectors I, j, and k respectively. Okay, so the unit vector I is here. So here's the unit vector I on the x-axis. And so there's an angle between I and M. So it's actually like on a diagonal plane, right? So this is the hard part it's hard to visualize. From vector M to vector I on this diagonal plane is what we call alpha. So then we also have in the back here vector J. So here's vector J along the y-axis. And the angle between the vectors, so again, you're dealing with a plane that's on a diagonal. The angle here between vector M and the unit vector J is beta. Wow, it really did not give me enough room. Beta. The angle between vector M and the unit vector J. And then here's vector K, the unit vector. And this angle between M and K is gamma. So it's really hard to visualize this without a three-dimensional model. Okay, so here's what you need to know. If I take the dot product of M times I, we know, based on the definition of the dot product, this is the magnitude of M times the magnitude of I, cosine, in this case, alpha. Similarly, the dot product of M times J is the magnitude of M times the magnitude of J, cosine beta. And the dot product of M and K, magnitude of M, magnitude of K, cosine gamma. Okay, now, we know that I, j, and k are unit vectors. So the magnitude of I, I'm going to write this. Since I, j, and k are unit vectors, then the magnitude of I, the magnitude of j, and the magnitude of k are all equal to what? 1. So a unit vector has a length of 1. Okay, so then I can replace all of these things here, I, j, and k magnitudes with 1. So we have the magnitude of M times cosine alpha, magnitude of M cosine beta, magnitude of M cosine gamma. Now if I take M times I, I get the coefficient here. Right, so if I multiply m times I, so m is A, B, C, and I is 1, 0, 0, then what's m times I? A. So what's the dot product of m times j if I have A, B, C times 0, 1, 0? B. And m times k if I have A, B, C times 0, 0, 1, I get C. So we're going to merge all these things together. So m times I is equal to A. So we're going to do this. A equals the magnitude of m cosine alpha. And we have the dot product of m times j, which is B. This is the magnitude of m cosine beta. And C is equal to the magnitude of m cosine gamma. And so then, therefore, you can find alpha, beta, and gamma with the cosines of m. Bless you. So cosine alpha is going to be A over the magnitude of m. Cosine of beta is going to be B over the magnitude of m. And cosine gamma is going to be C over the magnitude of m. And how do you find the magnitude of m? A squared plus B squared plus C squared. Okay, these right here are what we call the cosines of m. And if you want to solve for the direction angles, you take the inverse cosines. So let's do an example. Okay, it's all very formulaic, but I wanted to sort of prove to you where these things are coming from. It's not just some magical process. I mean, I guess it is. Math is pretty magical. If you like logic and stuff that makes sense. But I don't want you to just think like they're just magically appear out of nowhere. They actually have a basis in reality. Okay, so here's an example. Let's find the direction angles, the direction cosines, and the direction angles of vector v. Okay, so the cosine of alpha is going to be A over the magnitude of v. Cosine beta is going to be B over the magnitude of v, and cosine gamma is going to be C over the magnitude of v. So first of all, maybe we should find the magnitude of v. So let's see, 25 and 144 and 169. Well, don't work too hard. 169 plus 169. In simplest radical form, what is this root? 13 root 2. Okay, so cosine alpha is going to be A, which is negative 5 over 3 root 2. And cosine beta is going to be 12 over 3 root 2. You can certainly reduce that if you'd like. And cosine gamma is 13 over 3 root 2. These are the direction cosines. Oh, yeah. Thank you. It is 13 root 2. And you can reduce these. Right, this one for sure, 1 over root 2. You can leave the root in the bottom if you really want to rationalize. You can rationalize. So then now we want to find the direction angles. So we're going to take the inverse cosine and get alpha, beta, and gamma. What do you get for alpha? Nearest tenth? 105. Is it 0.8 or 0.7? 0.8. Beta? 49.3. And gamma? 45. And so these are your direction angles. Bless you. Okay, so a couple little thing about the direction angles. The direction angles uniquely determine the direction, but not the length of V. But if you know, I'm just going to not say this here. If you know the length of V, then let's see, the A component would be the magnitude of V cosine alpha. So for like what this little statement here is all about is if you wanted to find the components of V, you could find A, B, and C if you know the magnitude of V and you know what the direction angles are. So you could work backwards. And there is a relationship between the cosines when you're in 3 dimensions. And this property is really helpful, especially for an example like we're going to see next. If you know 2 of the angles, you can find the third. So here's the relationship. Cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. And so you can use this property of the direction angles. If you know 2 angles, you can find the third. Okay, so our last example for today says, given the direction angles of a vector, beta equals 2 pi over 3 and gamma equals pi over 4, find the acute angle for alpha. So, using this property here, cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. So cosine of alpha squared, plus cosine of 2 pi over 3 quantity squared plus cosine of pi over 4 quantity squared equals 1. So what is the cosine of 2 pi over 3? Negative a half. And the cosine of pi over 4? Root 2 over 2. So we're going to square these things. We get 1/4 and 1/2. Move everything to one side. And what do you get? 1/4. Square root that. Take the inverse. Yeah, so you've got all these possibilities. Oh, am I missing one? Pi over 3, 2 pi over 3. Four, thank you. Which one do I want? Yeah, the acute one. So, you've got two parts to the homework for the weekend. The critical one is the worksheet, which I'm going to hand you in just a second. That's due Monday, Tuesday. It's in prep for your quiz, covering sections 8.4 to 8.6. All the vectors operations, your applications, those are all the boats and the planes and the velocity vectors of the wind. This is all the force, the work, the dot product, the idea of orthogonal, and then the three-dimensional stuff, points and distance and spheres. And then you've got some book problems. So if you want to practice with the stuff we talked about today, that's what you're going to cover on page 658. So let me get you your worksheet.